world we live in is awash with data that comes pouring in from everywhere around us. On its own, this data is just noise and confusion. To make sense of data, to find the meaning in it, we need the powerful branch of science. Essential to us to monitor our governments and our societies. But it was our rulers up there who started the collection of statistics in the first place in order to monitor us. In fact, the word statistics comes from the state. Modern statistics began 2 centuries ago. Once it got going, it spread and never stopped. And guess who was first? The Chinese have Confucius. The Italians have Da Vinci, and the British have Shakespeare. And we have the Tabellverket, the first ever systematic collection of statistics. Since the year 1749, we have collected data on every birth, marriage and death, and we are proud of it. The Tabellverket recorded information from every parish in Sweden. It was a huge quantity of data, and it was the first time any government could get an accurate picture of its people. Sweden had been the greatest military power in Northern Europe, but by 1749 our star was really fading and other countries were growing stronger. At least, though, we were a large power, thought to have 20 million people, enough to rival Britain and France. But we were in for a nasty surprise. The first analysis of Tabellverket revealed that Sweden only had 2 million inhabitants. Sweden was not only a power in decline, it also had a very small population. The government was horrified by this finding. What if the enemy found out? But the Tabellverket also showed that many women died in childbirth. And many children died young. So government took action to improve the health of the people. This was the beginning of modern Sweden. It took more than 50 years before the Austrians, Belgians, Danes, Dutch, French, Germans, Italians, and finally the British caught up with Sweden in collecting and using statistics.
It was called political arithmetic. That was a lovely phrase that was used for statistics. Governments could have much more control and understanding of the society, how it was working, how it was developing, and essentially so they could control it better.
It wasn't just governments who woke up to the power of statistics. Right across Europe, 19th century society went mad for facts. And despite its late start, Britain, with its Royal Statistical Society in London, was soon a statistician's nirvana.
I love looking at old copies of the Royal Statistical Society Journal because it's full up with such odd stuff. There's a wonderful paper from the 1840s which shows a map of England and the rates of bastardy in each county, and so you can identify very quickly the areas with high rates of bastardy. Being in East Anglia, it always makes me slightly laugh that Norfolk seems to top the bastardy league in the 1840s.
One of the founders of the Royal Statistical Society was the great Victorian mathematician and inventor Charles Babbage. In 1842, he read the latest poem by an equally great Victorian, Alfred Tennyson. Vision of Sin contained the lines, "Fill the cup and fill the can, have a rouse before the morn. Every moment dies a man, every moment one is born." So keen a statistician was Babbage that he could not contain himself. He dashed off a letter to Tennyson explaining that because of population growth, the line should read, "Every moment dies a man, and 1 1/16 is born." I may add that the exact figure is 1.067, but something must be conceded to the laws of meter.
In the 19th century, scholars all over Europe did amazing work in measuring their societies. They were hoovering up data on almost everything. But numbers alone don't tell you anything. You have to analyze them. And that's what makes statistics.
When the first statisticians began to get to grips with analyzing their data, they seized upon the average, and they took the average of everything. What's so great about an average is that you can take a whole mass of data and reduce it to a single number. And though each of us is unique, our collective lives produce averages that can characterize whole populations.
Let's see what Sweden have done. We used to boast about fast social progress. That's where we were.
In my lectures, to tell stories about the changing world, I use the averages from entire countries, whether the average of income, child mortality, family size, or carbon output.
Okay, I give you Singapore, the year I was born. Singapore had twice the child mortality of Sweden. It's the most tropical country in the world, a marshland on the equator, and here we go. It took a little time for them to get independent, but then they started to grow their economy, and they made the social investment. They got away malaria. They got a magnificent health system that beat both US and Sweden. We never thought it would happen, that they would win over Sweden. But useful as averages are, they don't tell you the whole story. On average, Swedish people have slightly less than 2 legs. This is because a few people only have 1 leg or no legs, and no one has 3 legs. So almost everybody in Sweden has more than the average number of legs. The variation in data is just as important as the average.
But how do you get a handle on variation? For this, you transform numbers into shapes. Let's look again at the number of adult women in Sweden for different heights. Plotting the data as a shape shows how much their heights vary from the average and how wide that variation is. The shape a set of data makes is called its distribution. The statisticians who first explored distribution discovered one shape that turned up again and again. The Victorian scholar Francis Galton was so fascinated, he built a machine that could reproduce it, and he found it fitted so many different sets of measurements that he named it the normal distribution. Whether it was people's arm spans, lung capacities, or even their exam results, the normal distribution shape recurred time and time again. Other statisticians soon found many other regular shapes, each produced by a particular kind of natural or social processes. And every statistician has their favorite.
The Poisson distribution, the Poisson shape, is my favourite distribution. I think it's absolute crap.
The Poisson shape describes how likely it is that out of the ordinary things will happen. Imagine a London bus stop where we know that on average we'll get 3 buses an hour. We won't always get 3 buses, of course. Amazingly, the Poisson shape will show us the probability that in any given hour we will get 4, 5 or 6 buses or no buses at all. The exact shape changes with the average. But whether it's how many people will win the lottery jackpot each week or how many people will phone a call center each minute, the Poisson shape will give the probabilities.
So statisticians use shapes to reveal the patterns in the data. But we also use images of all kinds to communicate statistics to a wider public. Because if the story in the numbers is told by a beautiful and clever image, then everyone understands. of the pioneers of statistical graphics, my favorite is Florence Nightingale.
There are not many people who realize that actually she was known as a passionate statistician and not just a lady of the lamp. She said that to understand God's thoughts, we must study statistics, for these are the measure of his purpose. Statistics was for her a religious duty and moral imperative. When Florence was 9 years old, she started collecting data. Her data was different fruits and vegetables she found, put them into different tables, trying to organize them in some standard form. And so we have one of Nightingale's first statistical tables at the age of 9.
In the mid-1850s, Florence Nightingale went to the Crimea to care for British casualties of war. She was horrified by what she discovered. For all the soldiers being blown to bits on the battlefield, there were many, many more soldiers dying from diseases they caught in the army's filthy hospitals. So Florence Nightingale began counting the dead. For 2 years, she recorded mortality data in meticulous detail. When the war was over, she persuaded the government to set up a royal commission of inquiry and gathered her data in a devastating report. What has cemented her place in the statistical history books are the graphics she used, and one in particular, the polar area graph. For each month of the war, a huge blue wedge represented the soldiers who had died from preventable diseases. The much smaller red wedges were deaths from wounds, and the black wedges, deaths from accidents and other causes. Nightingale's graphics were so clear they were impossible to ignore.
The usual thing around Florence Nightingale's time was just to produce tables and tables of figures. I mean, absolutely really tedious stuff that, unless you're an absolutely dedicated statistician, it's really quite difficult to spot the patterns quite naturally. But visualizations, they tell a story. They tell a story immediately. And the use of colour and the use of shape, can really tell a powerful story. And nowadays, of course, we can make things move as well. Florence Nightingale would have loved to have played with. She would have produced wonderful animations, I'm absolutely certain of it.
Today, 150 years on, Nightingale's graphics are rightly regarded as a classic. They led to a revolution in nursing, healthcare and hygiene in hospitals worldwide, which saved innumerable lives. So, with statistics we can begin to see things as they really are. From tables of data to averages, distributions and visualizations, statistics gives us a clear description of the world. But with statistics we cannot only discover what is happening, but also explore why, by using the powerful analytical method correlation.
Just looking at one thing at a time doesn't tell you very much. You've got to look at the relationships between things, how they change, how they vary together. And that's what correlation is about. And that's how you start trying to understand the processes that are really going on in the world and in society.
Most of us today would recognize that crime correlates to poverty, that infection correlates to poor sanitation, and that knowledge of statistics correlates to being great at dancing. Correlations can be very tricky.
I got a joke about silly correlations. There was this American who was afraid of heart attack, and he found out that the Japanese ate very little fat and almost didn't drink wine, but they had much less heart attacks than the Americans. But on the other hand, he also found out that the French eat as much fat as the Americans, and they drink much more wine, but they also have less heart attacks. So he concluded that what kills you is speaking English.
The best example of a really groundbreaking correlation is the link that was established in the 1950s between smoking and lung cancer. Not long after the Second World War, a British doctor, Richard Doll, investigated lung cancer patients in 20 London hospitals, and he became certain that the only thing they had in common was smoking. So certain that he stopped smoking himself, but other people weren't so sure.
A lot of the discussion of the early data linking smoking to lung cancer said, well, it's not the smoking, surely that thing that we've done all our lives, that can't be bad for you. Maybe it's genes. Maybe people who are genetically predisposed to get lung cancer are also genetically predisposed to smoke. Maybe it's not the smoking, maybe it's air pollution, that smokers are somehow more exposed to air pollution than non-smokers. Maybe it's not smoking, maybe it's poverty. So now we've got 3 alternate explanations, apart from chance.
To verify his correlation did imply cause and effect, Richard Doll created the biggest statistical study of smoking yet. He began tracking the lives of 40,000 British doctors, some of whom smoked and some of whom didn't, and gathered enough data to correlate the amount the doctors smoked with their likelihood of getting cancer. Eventually, he not only showed a correlation between smoking and lung cancer, but also a correlation between stopping smoking and reducing the risk. This was science at its best.
What correlations do not replace is human thought. You've got to think about what it means. I mean, what a good scientist does, if he comes up with a correlation, is try as hard as she or he possibly can to disprove it, to break it down, to get rid of it, to try and refute it. And if it withstands all those efforts at demolishing it and it's still standing up, then cautiously you say, we really might have something here.
However brilliant the scientist, data is still the oxygen of science. The good news is that the more we have, the more correlations we'll find, the more theories we'll test, and the more discoveries we are likely to make. All around us are sensors continuously measuring temperature, water flow, and ocean currents. And high in orbit are satellites busy imaging cloud formations, forest growth, and snow cover. Scientists speak of instrumenting the Earth. And pointing up to the skies above are powerful new telescopes mapping the universe. The vast amounts of data we have today allows researchers in all sorts of fields to test their theories on a previously unimaginable scale. But more than this, it may even change the fundamental way science is done. With the power of today's computers applied to all this data, the machines might even be able to guide the researchers. Many of the dynamics of the natural world, like the interplay between the rainforest and the atmosphere, are so complex that we don't as yet really understand them. But now, computers are generating literally tens of thousands of different simulations of how these biological systems might work. It's like creating thousands of hypothetical parallel worlds. Each and every one of these simulations is analyzed with statistics to see if any are a good match for what is observed in nature. The computers can now automatically generate, test, and discard hypotheses with scarcely a human inside.
This new application of statistics will become absolutely vital for the future of science. It's creating a new paradigm, if you like, in science and the way in which we can do science, which is increasingly, which one might characterize as data-centric or data-driven, rather than being hypothesis-driven or experimentally driven. So it's exciting times in terms of the science, in terms of the computation, and in terms of the statistics.
Could statistics even make sense of your feelings? In California, where else, one computer scientist is harvesting the internet to try to divine the patterns of our innermost thoughts and emotions.
Well, this is the Madness movement. The Madness movement represents a skyscraper view of the world. Each of these brightly colored dots is an individual feeling expressed by someone out there in a blog or a tweet. And when you click on a dot, it explodes to reveal the underlying feeling of that person. This is what people say they're feeling today. Better, safe, crappy, well, pretty, special, sorry, alone. So every minute We Feel Fine crawls the world's blogs, takes all the sentences that start with the words I feel or I am feeling, and puts them in a database. We collect all the feelings, and we count the most common. They are better, bad, good, right, guilty, sick, the same, like shit, sorry, well, and so on. And we can take a look at any one feeling and analyze it. Right now, a lot of people are feeling happy. We can take a look at all the people who are happy and break down by age, gender, or location. Since bloggers have public profiles, we have that information, and so we can ask questions like, are women happier than men? Or is England happier than the United States? As people get older, they get happier. And moreover, we find that for younger people, they associate happiness more with excitement. And as people get older, they associate happiness more with peacefulness.
And we also find that women feel loved more often than men, but also more guilty, while men feel good more often than women, but also more alone.
As people lead more and more of their lives online, they leave behind digital traces. And with these digital traces, we can begin to statistically analyze what it means to be human.
So where does all of this leave us? We generate unimaginable quantities of data about everything you can think of, and we analyze it to reveal the patterns. And now, not only expert, but all of us can understand the stories in the numbers.